So now that we've learned how to calculate molarity, we can start to incorporate this into calculations that involve reactions. So we'll start with a case of stoichiometry, but after that, we're going to get into titrations, which are a calculation that we need concentrations for that involve acids and bases. So if we have this reaction, aluminum plus copper sulfate, and I've already gone ahead and balanced this one for you, react to form aluminum sulfate plus copper. We're now going to ask how much aluminum in grams is oxidized by 76 milliliters of 0.16 molar copper sulfate. And this is a more realistic situation for a question like this because if we're using something like copper sulfate, chances are it's going to be as a solution, not necessarily as a solid. But it's really the same thing we did when we did stoichiometry previously. We need to go from whatever we're starting with, which in this case is volume, into moles. Once we get into moles, everything else is the same as what we've done before. So 76 mils copper sulfate. Now since we're working with molarity, we do need to be in liters, so 1 liter over 1,000 milliliters. And then we're going to convert to moles. Molarity, which is the unit we have here, is moles per liter. That's literally how we calculate it. So even though it's written as molarity, it can be a conversion factor to go from moles to liters or liters to moles. So this is 0.16 moles per 1 liter. And now we're in the spot we're used to being in. And we can go from moles of copper sulfate, and we get that from our coefficients, to moles of aluminum, and then 27 grams of aluminum per 1 mole. All right, but what I really want to focus on in this section is the idea of a titration. A titration is using of a solution for which we know its concentration. To find the concentration of an unknown solution. And what we're going to be talking about here are what we call acid-base titrations, where we know the concentration of either the acid or the base, and we use it to find the other concentration. In order to do that, we use a piece of equipment that we've pictured here. This is known as a burette. And in the most common type of acid-base titration, we would fill up our burette with base. And then down here, we'd have an Erlenmeyer flask with some amount of our acid. And there's a couple different ways you can do it, but easiest way, most common method, is that to our acid, we're going to add a compound known as phenolphthalein. Well, phenolphthalein is a compound that has some interesting properties to it. If you put phenolphthalein into an acidic solution, phenolphthalein will be colorless. You won't have any way to see that it's there. But if your solution is basic, it'll turn pink. So what you do in one of these types of titrations is you'll measure out your acid, you'll add it to the Erlenmeyer, and then you'll put in a couple drops of phenolphthalein. From there, you can fill up the burette with base, and you very carefully mark down to the correct number of significant figures the point that you're starting at. And then you start adding the base into your acid. What you'll often see early on is you'll see some brief glimpses of pink, and as you swirl it or mix it, they'll go away. And as you get closer to the end of the titration, it'll take longer for that pink color to go away. Finally, at some point, you'll add a drop, and the pink color will just stay. It will not go away at all. That's the point where you know that you've completed the titration. And you then record the volume on the burette a second time, and the difference in those two amounts is how much base you've added. So assuming that you're working with just a base like sodium hydroxide, not something that's dibasic, and that you're using a monoprotic acid, that point where your solution turns pink and stays pink is the end of your titration. And it's the point where you know that you've added equal moles of acid and base. When you know you've added equal moles of acid and base, your titration is complete. And at that point, you can use mole calculations to figure out what the concentration was of the solution that you didn't know. So let's look at an example of how we would then calculate this. So we're going to start with an HCl solution that is 0.10 molar. The sodium hydroxide solution, we don't know. Now, in the end, the calculation we're going to be able to use, because we know it's equal number of moles, is that the concentration of the HCl times the volume of the HCl will equal the concentration of the sodium hydroxide times the volume of the sodium hydroxide. So this value, the molarity of the sodium hydroxide, is what we're trying to find. The molarity of the HCl is given, and then the volumes are values that we're going to figure out experimentally. anytime we do a titration, we're going to run multiple trials. How many? We typically want to do it until we get 3 results that are relatively consistent. So in this case, we're going to say that we ran 4 trials. We're going to keep all of our volumes in milliliters. And so in every case, we're going to use 10 milliliters of HCl. In trial 1, to reach the end of the titration, took 6.3 milliliters of sodium hydroxide. Trial 2, 6.19 milliliters. Trial 3 took us 8.27 milliliters, and our last trial, 6.24 milliliters. So what we can then do is, well, we can actually do this in 2 different ways. We can calculate a molarity for sodium hydroxide for each one of these 4 trials and then average them. Or we can average the volumes and then calculate the molarity from the average volume. But before we do that, the first thing I'm going to do is I'm going to take that trial 3 and I'm just going to get rid of it. Why am I getting rid of it? Well, the other 3 trials are within about 1/10 of a milliliter of each other, and this one's almost 2 milliliters higher. So it's way out of line with the rest of our results. So at that point, I can be confident in saying, yeah, we probably messed something up in trial 3, and we're just going to ignore it. So now I've got 3 trials remaining, and I'm going to average those 3 results. And if I do that, I get an average volume of 6.21 milliliters. Now all I need to do is plug everything into this equation here, and we get our molarity of HCl times the volume of HCl. I don't need to convert it. You might be wondering, do I need to convert it to liters? And in an equation like this, I don't need to, as long as I use the same unit on both sides of the equation. Because if I use milliliters here and here, when I divide both sides by 6.21, it's just going to cancel out. So I can use any unit I want there for volume, again, as long as it's the same unit on both sides. So I'm going to divide by 6.21, and I get the molarity of sodium hydroxide is 0.16 molar. All right, let's do one more example. But in this case, we're going to use sulfuric acid. And that's going to make things a little bit different because sulfuric acid is diprotic. So that means 2 moles of sodium hydroxide are needed to react with 1 mole of sulfuric acid. And we're going to say in this case we started with sulfuric acid that we knew was 0.20 molar. And each of our we ran 3 trials here. And we needed, or in each case, we used 20 milliliters of sulfuric acid. The sodium hydroxide is what we're trying to figure out. And again, here's our results from our 3 trials. So again, we can average. Our 3 sodium hydroxide values are all very close together, so they're all good results. We don't need to discard any of them. And our average sodium hydroxide, 14.28 milliliters. Now, it's not quite as simple as the previous example because we have this 2-to-1 mole ratio. So the moles of sulfuric acid here are 0.20 moles times 0.0200 liters, or 0.0040 moles. But if you look up at our stoichiometry, it's 2 moles of sodium hydroxide for 1 mole of sulfuric acid. So that means moles of sodium hydroxide are actually equal to 2 times that, or 0.0080 moles. So now we know the moles of sodium hydroxide used. We already calculated the average volume on the previous page, 0.01428 liters. And if we divide that, we get 0.0560 molar.